What is inventory model? Inventory model is a mathematical equation or formula that helps a company in determining the economic order quantity and the frequency of ordering. The company needs to maintain the inventories in order to keep good attachment with the customers. This model can figure out the quantity of the inventory should be restocked and when should the company restock the inventory. Renewal strategy are two non-negative basic numbers s and s greater than s. If the end-of-period stock quantity is not greater than s, an adequate stock to expand the amount of stock available up to the level s is quickly acquired. The inventory policy is when the inventory level drops to reorder point, more units are placed in order to replenish inventory. It is to examine the inventory system where there are considerable uncertainty about future demand. The stock levels at two consecutive periods are connected by the relation. Assume that the successive demands are independent random variables, then the stock values constitute a Markov chain whose transition probability matrix. A camera store stocks a particular model camera. Orders may be placed on Saturday night. The cameras will be delivered first thing Monday morning. The store uses an SS policy. If the number in inventory is less than S, order enough to bring the supply up to S. If the number of cameras in inventory is greater than or equal to S, do not order any cameras. The store set the policy with S equals 1 and S equals 3. If 0 cameras on hand on Saturday night, order 3 cameras. If 1 or more cameras on hand on Saturday night, do not order any cameras. XT equals number of cameras in inventory on Saturday night of week T. The possible values, states, of these random variables is 0, 1, 2, 3. Describe XT plus 1 as a function of XT, the number of cameras on hand at the end of the T week, under the S equals 1, S equals 3 inventory policy. X0 represents the initial number of cameras on hand, D1, D2, and so on represent the demand for this camera during the first week, second week, and so on, respectively. Assumed I are independent and identically distributed random variables having Poisson distribution with mean of 1. The random variables xt are dependent and may be evaluated iteratively by the expression. These conditional probabilities are called n-step transition probabilities. Thus, the n-step transition probability pi, j, n, is just a conditional probability that the system will be in state j after exactly n steps, time units, given that it starts in state I at any time t. When n equals 1, note that pi, j, 1, equals pi, j, to the power of 1. Because the pi, j, n are conditional probabilities, they must be non-negative. Since the process must make a transition into some state, they must satisfy the properties n-step transition probabilities in the matrix form. Note that the transition probability in a particular row and column is for the transition from the row state to the column state. When n equals 1, we drop the superscript n and simply refer to this as the transition matrix. Given that dt plus 1 has a Poisson distribution with a mean of 1. Thus, for the first row of P, we are dealing with a transition from state xt equals 0 to some state xt plus 1. Therefore, for the transition to xt plus 1 equals 3 or xt plus 1 equals 2 or xt plus 1 equals 1. A transition from xt equals 0 to xt plus 1 equals 0 implies that the demand for cameras in week t plus 1 is 3 or more after 3 cameras are added to the depleted inventory at the beginning of the week, so this implies that xt plus 1 is less than or equal to xt. So p, 1, 2 equals 0, p, 1, 3 equals 0, and p, 2, 3 equals 0. For the other transitions, For the last row of P, week T+1 begins with 3 cameras in inventory, so the calculations for the transition probabilities are exactly the same as for the first row. Consequently, the complete transition matrix is